Thank you to Sandeep, Piyush, and Vivek, and all of the organizers for giving me a chance to present this work. Today, I am completely out of my natural habitat. This is not the kind of things that I am very comfortable with. This is basically the result of my stay at Lund University for the past 2 years. And during many of the conversations with Jonas at Lund University, initially we used to talk about politics. Slowly it went into probability, and then this is the result. It's an ongoing work. We haven't finished the full thing yet. So I'm basically presenting partial results. I'd be really very happy if you have any feedback on the kind of things that I'm going to talk about. So there are a couple of things that I'll be that you may have already seen in this meeting thus far. An adaptive scheme for MCMC in infinite dimensions. Infinite dimensions is the only new object in this talk. Adaptive schemes, we have had Professor Fort talk about adaptive schemes and ergodicity of adaptive schemes. Professor Molan is also an established authority in this subject, so I would stay away from making any controversial statements. So the general theme is basically trying to come up with some schemes to sample from distributions which are defined on function spaces. So let us begin. The motivation, there are many. I'm going to be talking about only one specific motivation, which basically stems from Bayesian inverse problems. In this setup, there is a forward model, which is basically like a solution of a PDE. I will give you an example also on the next slide. And that is a forward model. And then you have some noisy observations on this. The goal is basically to estimate U, which is the input, using these observations Y. It's a standard statistical inverse problem. Any estimation problem is this. Every time we have any estimates, we are basically solving an inverse problem. A Bayesian approach would basically make us impose some distributional information on this U, meaning that not all the U's are equally likely. There are some U's which have some specific probability of appearing, and thus we use that information, which is usually the practitioner's information, to encode the prior on U. So now the problem is that I have some information on what is the distribution of U, and that is given to me. Now I have some information, basically the observations Y, which are noisily observed. I know that this is the model. And I also know the distribution of this noise. So that's my assumption. Now, given all these, the goal is to say, is to answer the same question, but this time in a probabilistic way. We would say that the solution to this inverse problem would be basically the posterior distribution. The posterior distribution of U given Y is proposed as a solution to this inverse problem. There are many issues when you are working on Bayesian inverse problems. Many of these issues stem from consistency or stability type of results. But we are not going to be talking about those kind of problems here, but we are saying that, let's say that we have actually solved the problem per se. We have basically gotten a closed form expression for the posterior distribution. Now what do we do? In practice, when we are actually doing these things on computer, we have to basically start sampling, or have to have some idea of how to sample this from this posterior distribution. In many cases, it so happens that this sampling is not so easy task. And we have seen these examples, some of these examples in the two courses that were given last week by Professor Fort and Professor Moline. And so I don't need to really give you a lot of a motivation on why do we really need to worry about this kind of thing. So just to give you a very specific example, this is a famous Calderon problem, but boiled down to one dimension. This is the Calderon problem, which basically says that this is Laplacian in the gradient form. So you have a unit interval 0, 1. I did not mention it. So it should be, so this is defined for x in the interval, in the closed interval 0, 1. In this interval, this is some sort of the density of matter on this interval 0, 1. And then you are solving some sort of a diffusion equation on this domain. The forward problem says that given this kappa, can you tell me what the value of P is? The e to the power of kappa is some sort of a density or profile of the domain. And the goal is to solve for this, solve this equation, given kappa. I have just given you the solution here. It's a very easy problem once you know the solution, but in higher dimensions it becomes a serious problem. And there are several versions of this problem. You can actually start thinking that you can complicate this by looking into a higher dimensions, making the domains a little more arbitrary, not so smooth, and so on and so forth, and there are different kinds of problems over there. But our goal is to basically extract the forward model, and the forward model in this particular case is given kappa, given the profile, I generate these values. What are these values? These are basically the functional values of this solution evaluated at certain points in the interval 0, 1. This is my forward model. So you feed kappa and the output is these k numbers. I'm very sure the k is actually capital N on the next slide. So the map is, so the map is basically going from give me a function and I'll output a vector of numbers. The inverse problem is now try to estimate kappa given these noisy measurements. So these are the true measurements, but then in the inverse problem, in the statistical inverse problem setup, we do not have these exact measurements. What we have is noisy measurements, and so given the noisy measurements, can I reconstruct my kappa? Okay, so that's the inverse problem, the statistical inverse problem.
So kappa is u, is like u.
Kappa is like u, yeah. In this language of observations, having like finite observations, this was analyzed in Acta Numerica paper by Andrew Stewart in 2010. The paper basically is a huge document on Bayesian inverse problems. He provides a complete analysis starting from the formulation of a problem, Bayesian inverse problems in infinite dimensions, to application of this whole theory to specific examples. And this is one specific example that he discusses in this paper. And the setup that he uses is that this G, the forward map that we saw on the previous slide, is basically like a map going from continuous functions to Rn. So that's what I said, that K is definitely going to be N, and it is N. So this is, we don't need any fancy mathematics to conclude that this is not an invertible map. If it were an invertible map, we would not even need this Bayesian setup, and we would just go back to our usual deterministic inverse problem and we'd just invert the map. But it's not the case, and that's where the Bayesian inverse problem setup, or the framework of Bayesian inverse problem, actually really gains a lot, because it works even when the maps are not invertible. And in this particular setup, even though we have such a huge dimensional mismatch, it is known, he proves that there is some sort of a regularity property for G. It is Lipschitz, and it does satisfy certain growth conditions. So now, if I were to write just expression, write these noisy measurements of Pxk as a vector y, and if I assume that the noise is mean zero Gaussian with covariance operator given by gamma, or covariance matrix in this specific case, then the likelihood of y given kappa can be written as this. Really nothing fancy happening here. We all know about this. The next is, now if you impose some more information that is prior on U, then you can again use basic Bayes theorem and just conclude this, that the posterior measure, which is a measure on the function space, is absolutely continuous with respect to the mu naught, which is the prior that you have imposed on the function space, and the Redon-Nikodym derivative is proportional to this quantity, which is exactly the same as above. So we have got...
How do you evaluate the constant that goes with this?
In this specific case, we do not care for the constant because we are going to be sampling. So we don't really care for the constant, as long as it is integrable, that's it.
You don't want the constant?
We don't want to know the constant, we don't care. All right, so in this specific case, we have a very nice expression for the posterior, and now the question is, can we sample from this distribution? Point to note here is that we could, so the question was to be able to build samplers to generate samples from distributions on function spaces. Here we have an example of a distribution on function space, and it is of a specific type. The type is very crucial here, that it is basically as a Gaussian type distribution. What Gaussian type distribution basically means is that the measure which is of interest is absolutely continuous with respect to some Gaussian known measure, and the Redon-Nikodym derivative is something nice. So some of the takeaways from this example is that, firstly, this is honestly an infinite dimensional problem. Okay, of course we can discretize the space, make it into a finite dimensional problem, but then of course we all know that we will lose some things when we are approximating an infinite dimensional system or infinite dimensional problem via finite dimensional setup. So there is something to be talked about over there if one were to use finite dimensional analysis. And then there are also similar kind of problems which appear in Lagrangian data assimilation. Amit is sitting here in the corner and he works on these kind of things. Signal processing, many of you are already familiar with. And then geophysics. These are all the kind of examples which are discussed in Stewart's paper 2010. Now, so after having, as I said, after having proposed the posterior distribution as a solution to Bayesian inverse problem, the next step is to be able to generate samples from this kind of a distribution. So that is now the center stage. So now we have come to the main backbone of this talk, that why do we need samples from distributions in function spaces? So now, from whatever we have learned in the last week, MCMC is the usual way to approach for generating samples in finite dimensional spaces is what we saw last week, but here we will be talking about MCMC in infinite dimensions. So just to very quickly rejig our memory, MCMC basically works like you generate a Markov chain whose invariant distribution is equilibrium measure is the target distribution. You generate samples long enough time, and therefore the ergodic theory kicks in, time average equals the space average. And then, so that's how you generate, you expect that the target measure is approximated. Of course, we know that the MCMC has some sort of a correlation problem, so which is why I introduce the Metropolis-Hastings step to possibly speed up the convergence of the sampler. Okay, so there are some issues to be dealt with before we even talk about infinite dimensional samplers. First thing is, how do we even talk about measures in infinite dimensions? All the analysis that we learned in school or in our college, always we learned about Euclidean measures on finite dimensional spaces. We talk about Gaussian measure on finite dimensional spaces, but we, unless we actually specialize to certain topics, we don't talk about measures in infinite dimension functional spaces. The one favorite thing we all are familiar with is Brownian motion. which is indeed an infinite dimensional object, we all are familiar with, but we don't really like to always go into the construction of Brownian motion all the time. So that's a bit of tricky business. So how do we characterize measures in infinite dimensions? So what kind of target measures are good enough for us? That's what we have to be very clear about. Next is, once we know what kind of target distributions, we have to generate, we have to construct a Markov chain. That's a major step. And the third is, notice that in the MCMC algorithm, when you actually use the algorithm to generate the samples and invoke the Metropolis-Hastings acceptance rejection step, you use this knowledge that you have all the measures involved in this analysis are absolutely continuous with respect to the Lebesgue measure. And you never deal with the measure, but you actually always deal with the density. There is no density in infinite dimensions. So something has to take the role of Lebesgue measure in infinite dimensions. And that was a key. We actually saw it already, that some Gaussian measure. Because Gaussian measures, we know how to construct in function spaces. So we have quite a bit of heavy analysis, which we already know about Gaussian measures. So why don't we use that? So that's to begin with. Usually, it's a tough task to define Gaussian distributions in function spaces, except when we already know something about the object, some regularity, differentiability, integrability, and so on and so forth. And using that, we can impose some basis and therefore restrict them to a certain class of function spaces, and then impose some Gaussian measures or other measures of your favorite type on those function spaces. Typically, that is done using some Mercer expansion, or if it is in Gaussian case, it is using the Kahneman-Loewe expansion. Okay, both do exactly the same. They are talking about L2 expansion of random fields. Kahneman-Loewe is for Gaussian, Mercer is a little generic. So some just examples, some of the known infinite dimensional random elements that we are familiar with: fractional Brownian motion, OU process, Gaussian random fields, and so on and so forth.
These are all things which have finite parametric differentiation.
No. No. For example, Brownian motion, you have to have the covariance, the Kahneman-Loewe expansion is infinite. And so I'm not saying that they are finite. I'm just saying that you have to have some prior information, like which space do you want to live in? That has to be very clear. So where are you constructing the measure on? So function space, which function space are you going to be working on? That has to be clear. So once you know that, you can build possibly using some information about the basis and so on and so forth. We are not doing in time, because time is just not a parameter at all. We are not going to be running in time. It's just one space. Yeah, and on a compact time interval, let's say. Exactly. Very good. Right? Exactly. So those kind of information has to be encoded into exactly. Okay. So G and the covariance have to have something in common. Okay. So we all know that if U is Gaussian and if G is a linear operator, then G of U is also Gaussian. We know that. But the covariance becomes very tricky. Covariance is G transpose of, so G, the covariance operator of the U, and then G transpose. And that is a very difficult object to deal with. We know that because if we know the eigenbasis of one matrix, and if we multiply that matrix with another matrix whose eigenbasis is also known, the product need not have any of the eigenbasis. It will have an eigenbasis of its own, something completely different. So these things are extremely very subtle, and these things have to be chosen by us, which is why it's sort of a cooked up type of a analysis when we actually have to do mathematically very clearly, because when you want to have some closed form expressions, you have to assume a lot of things, and these lot of things many times do not make sense. So we have to have this information. All right, so the state-of-art MCMC algorithms as of now deals with target measures which are of this type. If I'm talking about target measure, I should also say something about the space on which it is supported, right? So I will mostly be restricting myself to Hilbert spaces, okay? Separable Hilbert spaces so that I have a basis, okay? And mu naught will be a Gaussian measure which is supported on that Hilbert space with appropriate covariance. And it has to be supported on the Hilbert space, therefore the eigenvalues of C must be summable. Okay, so it's trace class operator. I have mentioned it here in this form, but if you remember in Professor Moline's talks about on Langevin dynamics, there was no y, it was only u. Y is just a parameter. Okay, in Bayesian inverse problems, y is basically the observation, so it just does come in as a parameter. And just as a language, phi is also called the potential. And if you just want to take a simple example, when the target measure itself is also a Gaussian with a shifted center, then this is the potential. The advantages of being in this framework, that first is we are dealing with Gaussian measures, and we know quite a bit about Gaussian measures already. So all that theory comes in handy in proving many, many theorems. And also, we just saw that the role of Lebesgue measure is replaced by the Gaussian measure. Okay? So that's very, very, very crucial to our analysis. Just once again, we are not talking about Banach spaces, we'll be focusing only on Hilbert spaces just because we have a nice basis and we have a expansion. So let's begin with the MC part of the MCMC, which is the Markov chain part. What kind of chains are we going to be talking about if we were to talk about MCMCs in infinite dimensions? Let's recall very quickly the Metropolis-Hastings algorithm. You start at some time, take x naught, okay, and then the next step, you are going to be proposing some random variable y using some kernel, okay, some measure which is supported on the function space. Given xj, you want to sample y. Once you have computed y, you have found out, you have sampled y, now you want to do something which is called the acceptance rejection step. You compute this quantity. Recall, so this expression used to be looking like a ratio of likelihoods, and that's why I'm writing like this. I'm not using densities, the language of densities at all, and that's very crucial, okay? So this is basically the Radon-Nikodym derivative of these two measures, which is nu perp and nu is the joint likelihood, nu perp is the switched likelihood. And then the rest of the steps are exactly the same as Metropolis-Hastings. So let's start with proposing a very simple model. Let's consider this, which is, if I am at step x, I propose a new, my new position, which is basically x plus beta xi, and xi is normal 0 c, where c is exactly the same as the covariance of the base Gaussian measure. It's the same c. And then I shifted that with x. Good point. Yeah, okay. So psi is supported on the Hilbert space, and x is also living in the Hilbert space. Okay. And then beta is basically a step size controller. There is a problem now. Okay, so firstly, just to rewrite whatever we have written, there is a problem. The problem is that in the Metropolis-Hastings, the acceptance rejection step, we were computing this Radon-Nikodym derivative. And then for the Radon-Nikodym derivative, we know that there are some things which are well known for Gaussian measures, and we are in the Gaussian setup. Gaussian measures have this property of either orthogonal or absolutely continuous. Two Gaussian measures in infinite dimensions, they are either absolutely continuous or orthogonal. In this case, it so happens that this is going to be orthogonal. Why? Because the x does not live in the Cameron-Martin space. We know that the two Gaussian measures are going to be absolutely continuous if the shift is in the Cameron-Martin space. But here there is a problem. So you may think that, well, so there's no way I can go forward with this because my position is always going to be in the Hilbert space. My current position is always going to be in the Hilbert space. I cannot shrink it to go to a dense subspace of the full Hilbert space. So this is never going to work. But it turns out that there is a small tweak, and then this works okay, even though this is not in the Cameron-Martin, because we are not talking about the absolute continuity of only the kernel, but we are talking about the absolute continuity of the joint. So this works out. It's just like a trick. And then this is called the preconditioned Crank-Nicolson. And the acceptance probability turns out to be simply this expression, which is very simple. Also note that it does not depend on beta. There is a takeaway from here also. What is beta? For example, if I set beta to be 1, what happens? My proposal generation machine will always generate independent samplers. Okay, just does not care where my initial location is, just keeps generating independent samples. What happens when beta is 0? Forgets about anything new information, just stays where it is. So these two are sort of extremes. If this does not depend on beta, it says that basically this cannot be tuned. I cannot tune my beta. So for example, most of the time when you are running MCMC in practice, you set your acceptance rate at some level and then do this reverse calculation of finding beta. That beta which gives you your favorite acceptance probability. And this cannot happen because there is no beta here. Okay, so you cannot tune your algorithm. So we move on from the random walk type of proposals and we move to something called the stochastic Langevin dynamics in infinite dimensions. Similar thing was already seen previous week by Professor Moline. He gave extensive lectures on this Langevin dynamics in finite dimensions. The only difference you may notice that there is a operator L here which was missing in finite dimensions. This is because we are in the space-time scenario. This is the SPD. Okay? So that's the only difference. So some things to be said. B is Brownian motion on I. What does it really mean? It means white noise on Hilbert space. There is a problem. White noise is not supported on the space where you define, which is why we scale it. Okay, and these operators K and L, the script K and script L, are elliptic operators with some known regularity conditions so that they make sense. All this equation makes sense. Okay, most of the time, trace class is good enough when you have K inverse. K is trace class and L inverse. So that's what I write here, that K is usually said to be identity or L inverse, depending on the setup. And we will always take K to be L inverse. L, most of the time, is usually taken as some sort of a Laplacian, your favorite in the favorite space. And then there is also another parameter which is hanging around over here, which is gamma. And there are the invariant, this dynamics will have invariant measure for different values of gamma. So gamma equals 1, we saw in Professor Moline's lecture that it gives you the invariant measure, which is this. And if you set gamma to be 0, basically you drop the Langevin step, the gradient part is dropped, and what you get is the usual invariant measure. Okay? We want to use this dynamics to generate a Markov chain. We again saw last week, the usual way is Maruyama discretization, and we do something similar. something very funny happens over here, infinite dimensions. I don't have time to talk about that, that it depends on the scale at which you actually discretize. So when you are discretizing, it depends a lot on at which place you take your middle value, the mid value. And it matters a lot in this case. Turns out half is the value. If you move away from half, all hell breaks loose. So we generate this, which is basically a discretization of this equation. Just a bit of algebra. I'm not really, it does look a little different, but it's not really. So delta is basically the step, the discretization step, and psi is this discretized version of Brownian motion, which is a white noise here, and psi is still infinite dimensional. The discretization is happening only in time. Space is still full. Okay. So very common takeaway from this is two proposals. One is called the preconditioned Crank-Nicolson, which is setting gamma equal to 0, gives you exactly the same that we saw earlier. Next is pCNL, which is the preconditioned Crank-Nicolson Langevin, and that is obtained by setting gamma equals 1. The only difference between these two being that you actually are using the Langevin dynamics in this, whereas in PCN you were not using. You were just ignoring the dynamics altogether. Just to very quickly summarize what is known, it is no way exhaustive list. There are many papers, and we saw many of them which were presented in Professor Fort and Professor Moline's lectures. Most of them were in finite dimensions, but there are some connections with infinite dimensions, so you can actually use them. But in infinite dimensions, this is basically the broad status quo. So there is this paper of Harris, Stewart, and Voss. They talk about sampling, analyzing SPDEs and the path sampling from those problems. Besco-Stewart, it's generally talking about different kinds of problems where you may come across having to sample from infinite dimensional distributions. Besco's Robert Stewart Voss is, they talk about sampling Brownian bridges, diffusion bridges. So how to sample diffusion bridges? No, the full function. You want to sample the full function. Yeah, the full path. This is why we are in function spaces. So, and then, yeah, computer, very good. So the moment we come to move from notebook to computer, things change. We will come to that, yeah. So actually when we are doing it on computer, you do have to truncate at some level. And that basically begs the question, why are we doing this? If we are eventually going to be doing finite dimensional analysis, why am I standing here wasting my time talking about infinite dimensional analysis? Because in computer, eventually it is a finite dimensional analysis. Huh? Yeah, I'm also wasting your time. I'm sorry, actually that time is much more valuable than mine. I'm sorry, yeah. So, and in, I can't see the time. Yeah, so, yeah, and then there are some other papers which talk about further analysis. For example, Law talks about how to improve the efficiency of such algorithms. And then one very major contribution came in 2014, where Martin Herer, Stewart, and Vollmer, they actually estimated the spectral gap for PCN. And in this paper, they actually mention Vollmer's result, like just in passing, that Vollmer also works on non-Gaussian path priors. And then this is the paper that I just learned last week. Professor Fort mentioned that they actually talk about Wasserstein and chronicity in adaptive version of PCN. So what is adaptive now? They did not even talk about that yet. Okay, so our contribution, I'll start now in 9 minutes. The basic premise of adaptation is that we have some parameters hanging around in this proposal generating machine. Why don't we use those parameters to our advantage to efficiently sample, that is, increase the efficiency? So how does that going to work? There is this kappa which is hanging around, so script k. which can be chosen to be identity, can be chosen to be L inverse. But L was fixed again. So how do we do that? So what happens is, there's one more thing to be noticed here is that this phi, which was appearing as a potential, or the Redound-Nikodym derivative, this is usually not known. And computing this, so because my collaborator is actually a computational scientist, he talks about this computational times and all those things, and for him this is a major problem. Grad phi is not known. Computationally it's a too much of time taking task to even estimate those kind of quantities. I don't want to do that. That is another problem. So we want to use our information to somehow get around these kind of problems. Just to recall, this is the target density distribution. This is, in my language, this will be called the base measure. I will always call it base measure, with eigenvalues in this. Once again, in all the slides following, everything will be on the eigenbasis of this operator C. All the operators that you see are all simultaneously diagonalizable. So if you do not have simultaneous diagonalizability, we are in deep trouble. And this computer has stopped. I don't know how much time do I have. Blank screen. No, I don't want to. I don't want you to get delayed for your lunch. Okay, it stopped. Okay, so remember delta was the step size, the discretization in time. This is just some notation, just for concise expressions. I will denote M to be the posterior mean, that is the mean of the target distribution, and I'll define this quantity, which is lambda star, which is the scaling of the posterior. Okay, I will come to this a little very soon. The posterior mean and some sort of the posterior covariance has to be learned from data. Can we do this? Okay, so what we do is, we basically inspired from this paper, recall that there are two invariant measures for gamma equal to 0 and gamma equal to 1. Those two measures are Gaussian with L inverse as a covariance operator, and the other being, which is something which is proportional with respect to this measure. So, but the true target distribution, target measure was this quantity, right? But the new target, if what I want to do is, I want to change the dynamics so that I can actually also express the target measure with respect to mu, which was not the base measure, which is the new measure, which is the new Gaussian measure with L inverse. Remember, the base Gaussian measure is something that is known to me. The covariance operator is C. Yes, the covariance operator is L inverse, which is sort of again in my control. I can tweak that. So I express the new target measure as this. Okay, just rewriting, nothing new happening, just rewriting with respect to a new measure. And I use this, now I use this information to reset the K and L inverse. So I set my K, which was appearing here, is the scaling of the step size. I use that. So this I have the C half and C half, which is basically giving you, if I'm thinking of in terms of the eigenbasis, this is giving me the full Gaussian base variance. And then the lambda star is basically telling you some sort of scaling step. And I'm using the same, of course, mu naught star is going to be this quantity. Okay, sorry, there is a trouble. This is mu naught star, which is actually just mu. So I propose this new proposal, which is same as the usual pCN, but I have this extra term hanging around, which is sort of a drift term. Now, how is this drift term? You can stare at this term, which is basically a remnant of having used this formula. So I basically changed the phi in the Langevin dynamics. I changed the phi to a different phi. But I have this extra term, and that's a really bad term in some sense. In what sense it is a bad term? In terms of ergodicity, improving ergodicity, it's a nightmare. most of the algorithms which are available as of now for function spaces, ergodicity in function spaces, are often talking about when you have pCN type of measure. Whenever you have a M which is to be estimated and this M has no control, there is no bound available on M. If this is continuing to move on around in the unbounded space, I have no control on this. So proving ergodicity is a nightmare. But so this is basically, you can look at the Metropolis-Hastings ratio. A simplified version is this. A simplified version when we replace grad phi by M. This is what we get. What the thing that we are using is basically Fisher's identity in infinite dimensions, that expected value of grad phi will be related to M, the posterior mean. Okay, so we are basically doing that. And if we do that, now I can actually try to convince you that this is heuristically should be very helpful each time. And so let me give you the heuristic just a minute. So just stare at this proposal, move on, now adaptation. So M was a posterior mean which was not known to me. I have to estimate it. So this is how I estimate from my past samples. And now you can see that heuristically, given the past information, if my past samples have been accepted, they should have been good. They should be going in the right direction. So if they were accepted, I'm using them to generate my mean. So I'm basically pushing my proposal to go in the right direction. I'm pushing my algorithm to go in the right direction. So that basically helps me in heuristically saying that the proposal should quickly give me the target measure. And how do we actually mathematically make this precise? Ergodicity, which is extremely hard. We could not do it. We are still working on it. It's still an ongoing process. But I do have some numerical results which I will anyway show you again. So how much time?
You go another 4 minutes.
Okay. Anyway, so now the question is, so there are many proposals in our paper. There are many more which you can just keep generating, because you just keep tweaking one more parameter, you get new proposal, and you tweak another parameter, you get new proposal. But how good are they? The thing is, this goodness has to be measured in terms of efficiency, ergodicity. But ergodicity in MCMC for infinite dimensional spaces, there are very few results. And when we come to adaptive schemes, there is actually none. We haven't come across any paper which actually does adaptive MCMC, proves ergodicity of adaptive MCMC schemes on infinite dimensional spaces. We haven't come across. So this is what we are trying to actually work on. There appears to be some sort of hint which comes from Heyer's paper, but Heyer's paper, Heyer, Stewart, and Voss, in that paper, in their conclusion, they actually say that if your proposal is not symmetric, that is, if you have extra drift, none of the machinery which is developed in the finite dimensional cases will work to prove ergodicity. So it's not a mathematical statement, but they actually say it in their conclusion that the finite dimensional machinery will break down if you want to do for this extra M hanging around. So it's not my statement. I'm just attributing it to them. We are still struggling how to prove ergodicity, but a bit of cheating, because anyway, I can blame it on my co-author, because my co-author is again a very heavily computational guy. For him, ergodicity really does not matter. For him, what matters is numerically it converges. I can see it. So for him, that is a proof. So what he say, I mean, of course, this numerical community, they often do this, is they say that adaptation, we don't need to adapt all the way throughout the time. You can actually truncate. You can just stop. Adapt for 100 steps and stop. And then let the chain go on from there. So once you have stopped and let the chain go on from there, adaptation is not happening. Therefore, the usual ergodicity type of results can be utilized. So you don't have this problem of uniform in theta ergodicity and so on and so forth. You don't have to deal with them. And then this can be dealt with. And this is precisely what is done in two papers Zheng and Li. This is the last term, and this is the proposal with extra drift, need really extra care. So this is just an example. I can explain it better if you are interested. This is something that, I mean, I'm sure that I will be doing a very shady job at explaining it here in just a minute because I don't want to waste your time. Basically, you have a field which is generated, it's a Gaussian random field, and you are having some observations, okay, which are some sort of noisy observations, you can think of them. And then the goal is to sample U, which is the real field, the total field, given these observations yi. Okay, so what am I looking at? This is basically showing you how the lambda, the lambdas, which were basically the scalings, are working for different proposals. I'm basically showing it for M grad, which is the red dashed line. M grad is a proposal which was developed by see, I can't say those names. I will just show you the names. These are the two people. Pitsias and Papas. Sorry. So this was developed by them, and until their paper, numerically speaking, they were the best known algorithms. Our basically seems to show that we are actually doing a bit better in terms of scaling the eigenvalues, and this is basically the performance chart, which you can just look at. Here, ESS is the effective sample size, and as I said, higher beta. So the way this chart has to be read, the way it has to be read is you set the acceptance probability rate at a fixed level. That you say that my acceptance probability is 0.2. For that 0.2 to be achieved, how should you keep updating your beta? Okay, so the sooner beta becomes 1, that means that you are forgetting, you are okay with forgetting your present position and keep independently sampling. That basically is a way of concluding that you have sort of forgotten the past and therefore ergodic. Okay. So just one question which we already talked about. We are talking about infinite dimension analysis, and we are talking about computers. Computers don't know anything about infinite dimensions. They only work on finite dimensions. So what am I doing here? Why are we even talking about this thing? Actually, it's because I posed my question, so it is a very good question. But the thing is that actually this is looking at infinite dimensional space samplers is a better way to than looking at finite dimensional samplers if your problem is inherently infinite dimensional. The reason being that infinite dimensional samplers are dimension free. So the moment you increase your the mesh size or decrease your mesh size rather, you'll have to update your algorithm, and the algorithm may not work very well with respect to your mesh size. Infinite dimensional samplers basically tell you that forget about the mesh size altogether. You can truncate at a different level using the basis terms. Of course, the truncation in basis and the mesh size have something in common. Basically, one is of convolution with respect to some integral operator. So they do appear some sort of counterintuitive to one another, but for many of you who are working on Bayesian analysis, you are probably familiar with Bayesian misspecified models, and this is basically related to that. So if you do not, there are more problems when more observations lead to worse estimates, and that usually is done happens in Bayesian misspecified setups. So this is again just a chart to show that the beta is doing much better in this case when we are actually doing it using the infinite dimensional analysis, when we are not restricting ourselves to any specific truncation, and this is when you are looking at it as a finite dimensional problem that is after truncation. And that's it. Sorry I have taken it so much longer.